In question 3, when a clean metal surface in a vacuum is irradiated with ultraviolet radiation of a certain frequency, electrons are emitted from the metal. In A part 1, we need to explain why the kinetic energy of the electrons has a maximum value. Well, the energy is provided by the photons and is equal to hf, the Planck constant, multiplied by the frequency of the photons. Therefore, all electrons are given the same amount of energy. The amount of energy they need to escape will vary, and therefore so does the kinetic energy they come off with. In part 2, we need to explain with reference to the work function why, if the frequency of the radiation is below a certain value, electrons are not emitted. Well, the work function gives the minimum energy the electrons need to escape. If the photon energy is less than this, no electrons will escape. The photon energy is related to the frequency by photon energy E is equal to Planck constant h multiplied by the light frequency f. In part 3, we need to state a unit for the work function. Well, the work function is an energy and so is measured in joules. In B, light energy is incident on each square millimetre of the surface at a rate of 3.0 times 10 to the minus 10 joules per second. The frequency of the light is 1.5 times 10 to the 15 Hz. In B part 1, we need to find the energy of an incident photon. Well, energy is Planck constant times frequency. The Planck constant is given on the formula sheet, the frequency in the question, giving a photon energy of 9.9 times 10 to the minus 19 joules. In part 2, we need to find the number of photons incident per second on each square millimetre of the metal surface. Well, the number of photons per second will equal the energy per second divided by the energy per photon. This is 3 times 10 to the 10 joules of energy over 9.9 times 10 to the minus 19 joules of energy per photon, giving a number of 3.0 times 10 to the 8 photons. In C, we're told in the wave theory model of light, electrons on the surface of a metal absorb energy from a small area of that surface. In part 1, the light striking the surface delivers energy to the small area at a rate of 3.0 times 10 to the minus 22 joules per second. The minimum energy needed to liberate an electron is 6.8 times 10 to the minus 19 joules. We need to find the minimum time it would take an electron to absorb this amount of energy. Well, time is energy over power, and we need an energy of 6.8 times 10 to the minus 19 joules, and the power, or energy per second, is 3.0 times 10 to the minus 22. This gives a time of 2267 seconds, or 2.3 times 10 to the 3 seconds, to two significant figures, the same as the data we're provided with. In part 2, we're told that in practice the time delay found previously does not occur. We need to explain how this experimental evidence was used to define the particle model for the behaviour of light. Well, one particle or photon of light delivers its energy to one electron, and this releases it instantly. This instant release cannot be explained by the wave model of light.